I'm Alan Thorpe.
And I'm David Rogers, and together we host the WeatherPod.
In this special series on artificial intelligence, we invite leading experts to reveal how AI is being used across all sectors of the global weather enterprise.
We want to find out how business, the public sector and academia are using AI. Can it help improve the accuracy and quality of weather and climate information?
Can it help to make weather and climate information more useful and usable across a range of critical activities that are impacted by weather and climate?
There are many claims being made about AI, but what is its real value when it comes to helping business and society meet the growing climate challenge?
Our guest this episode is Florian Pappenberger, the Deputy Director General and the Director of Forecasts at the European Centre for Medium Range Weather Forecasts, ECMWF. Florian leads ECMWF's forecast department, and that's responsible for the production of weather forecasts, for forecast quality control, and for the development of novel forecast products. ECMWF has for a while been experimenting with using deep learning to produce a data-based AI weather prediction model. And last October, Florian played a key role in the launch of the Artificial Intelligence Integrated Forecasting System. This is ECMWF's first forecasting system, that incorporates a machine learning prediction module. In this episode, we delve more deeply into ECMWF's use of AI and how this may impact its future predictions, products and services, especially when it comes to their use by meteorological services and other customers in the developing countries. Florian, it's a great pleasure to welcome you to the WeatherPod to share some of your thoughts on how artificial intelligence is playing out in the weather prediction area.
Yeah, great to have you on the show, Florian.
Thank you very much to be here on this really rainy day.
Absolutely. I wanted to start actually, in a sense, before we delve into the machine learning aspects, by just talking a little bit about ECMWF's plans. Obviously, they're quite extensive, so you'll want to summarise them. But I think listeners will know that ECMWF is a major producing centre for weather ensemble, global weather prediction data. And it's used by many national meteorological services and companies and other users around the world so that they can construct weather forecasts. So, as I said, prior to us getting into the machine learning aspects, there are many other things where I know there are developments, like, for example, in model resolution or the complexity of the model that you have in your forward plan. So I'm sure users will be interested to know, in broad terms, what those plans are.
Yeah, it's actually a very great question. I sort of don't really know where to start and to stop, I have to admit, because it's a fairly wide field. It's a sort of a very simple answer. It's actually that resolution and complexity will keep increasing. That's how basic and simple it is. You may know now that we actually run an ensemble at 9 kilometers, and we don't anymore have this traditional high-resolution forecast. Having said that, actually, within the Destination Earth program, we already run a 4-kilometer single run, not an ensemble, every day with an initiative. And we're experimenting with a small ensemble around the 4 kilometers. So we're already trying to push the boundary significantly beyond those 9 kilometers. And we're doing the first evaluations at this scale. And as you sort of would expect, tropical cyclones and orographic precipitation or anything to do with orography, of course, sort of really improves. What else is going on? Well, we improved the dynamics, we improved the physical parameterization, we work on this kilometer scale resolution and simulations of trying to push it. We do lots of other sort of more traditional things like optimizing the most processes, evaluating non-hydrostatic effects, looking at model uncertainties, looking at the hydrology. And we also see how we can do a better trade-off between ensemble configurations. In sense of what's upcoming this year, we will have, for example, new reforecast configurations. We're going to change the reforecast configuration, which we have now. It will run every other day, so it will be twice, or currently runs twice a week. It will be running on every odd day in the future with a bit more ensemble members. And now this has an impact on a lot of people design products from that. We are starting a new seasonal forecast, so System 6, C6 is starting, which will have a large ensemble size and a higher forecast frequency too. It also will extend up to 2 years. So we will have a longer reforecast period. In the Copernicus area, we are currently adding the Bureau of Meteorology to this multi-model, so people can use more multi-models. And there's also, we discussed this week, the new reanalysis that's called ERA6. It will also come at a higher resolution, but it's also for the first time a one-way coupled ocean, atmosphere, land reanalysis.
So I suppose, Florian, what about areas where, in a sense, we're expanding out from just purely the weather in terms of the model, in terms of things like atmospheric composition, or I think you mentioned hydrology. What are the sort of additional sort of processes, if you like, or interactions that you foresee in the next few years?
So we will have more chemistry or more atmospheric composition in the normal weather forecast. Of course, we do already run the atmospheric monitoring system for the Copernicus services. That also will always, that sort of goes in step in terms of resolution and reanalysis. We will have more of that. We're going to run we're looking at the CO2 and how to measure CO2 and how to do attribution from CO2 in that sense. In the hydrology, there's many sort of very specific steps. Hydrology will be completely integrated, and we will have, for example, rivers in our model. I know this sounds fairly old-fashioned, but we will have rivers in our model. Actually, we'll predict river discharge directly from the atmospheric forecasts. So all of those components are increasing too in complexity, but also increasing in terms of applications in that sense. The last one, which I think is still quite important, sort of going a bit outside the remit, is, but the open data journey is of course continuing. By 26, we will have fully open data, which will be, I think, really important for many users who can't currently afford to purchase ECMWF products.
Just to be clear, when you say open data, do you mean freely available?
There will be a significant set of data open and free, and all data will be open. And then there will be, for some data, which we can't, due to technical reasons, make open and free, there will be a charge which recovers our costs.
And it's actual data, digital. I mean, there's a lot of imagery, right? You make
So
available,
the,
but
the images or the plots are already open and free, but it will be the raw data.
That's a big step for many, I think. So maybe we can go on and talk about our favorite topic of the day. So ECMWF, at ECMWF, you've been experimenting with using deep learning to produce data-based AI weather prediction model. And I think last October you launched the Artificial Intelligence Integrated Forecasting System, AIFS for short, which is your first forecasting system incorporating a machine learning prediction module. So what prompted this? And how does it work?
So I have to admit, what you described is absolutely correct. I'm always slightly offended because we did actually already start a machine learning strategy in 2021. So it's not something which came completely out of the blue, to be fair. It was looking slightly differently, admittedly. But we did do it for quite a while. And if you sort of go back to 2022, you suddenly have all these other publications popping up of trying to use machine learning in forecasting. And that sort of prompted us to re-look at machine learning and how it is done. And then I think we sort of very swiftly assembled experts around the topic and developed this AIFS forecasting system, which is very much based or very similar to the GraphCast Google one, but not the same in that sense. So that's sort of, the technology is sort of very similar to each other. We have at the same time, one of my big worries at the time was that you had all these papers claiming these successes of machine learning and how great they are, and they predicted that particular tropic cyclone, that precipitation, they were really good there. And I always dislike that. And the reason is because I think it doesn't really stand up to operational scrutiny. I really believe that papers and publications, scientific evaluations are a keystone, are very important. But if you really want to test a system, you have to test it in reality. And therefore, we actually started to run not just our own, we also run 4 other systems now, which are all open source in a real operational mode, and publish the results of different groups and teams around the world on our websites for comparison. And it's super interesting because the daylight, the operational reality is sort of really sanitizing the good and the bad and what it really works from in that sense. So I quite like it. Our model is also currently based or is slightly based on the reanalysis, but not just. It's also based on the operational analysis. The reanalysis is sort of roughly at 0.25 degree. The analysis is at significant higher resolution. We're sort of making 6-hour time steps and go out to 10 days. We've done experiments going out to sub-seasonal, so 45 days already. And these models are not too dissimilar, I would argue, to ChatGPT, that instead of learning connections between words, they learn the connections between the atmosphere in that sense. So that sort of prompted us. And if you look very carefully on our website, we also publish scores now for all of those. It's only a limited number currently on the website because it takes us a while to get it up. And there you can actually see the traditional ranking between the traditional models, but also with the machine learning models.
So what's been I mean, if you can summarize that quickly, I mean, what have you seen so far in terms of performance? I mean, how is it helping or otherwise?
In terms of performance, they're scarily good. We just have actually started working on a new version. So the AIFS model, sort of, to be fair, the version release is significantly higher than traditional weather forecast. It's still a very fast-moving discipline. So we tend to release, or we have a new version nearly every month at the moment, or every other month, to be fair, ready. The latest version I've seen improved precipitation so much, it's basically double the rate what we've seen. So we had 2 days improvement in precipitation. Scores and really SEEP scores, or proper station-based verification. And we all know that 2 days in traditional modeling did take us good 20 years usually, and we've achieved that in less than 4 months in that sense. So their scores are quite good. The other thing we are quite keen on is sort of more in-depth diagnostics. So that's very traditional evaluation. And we just looked at that, and we have these quarterly review meetings, and we made one very specific on the artificial intelligence models. And they are scarily good in predicting physical features which they haven't been really primarily trained on. So you look at error structures between our traditional IFS and you look at the AIFS, and they're not too dissimilar. They both have errors. For example, have precipitation errors around the tropics, which are very obvious, and they both display them. But if I were to give you these both different ones, I don't think, or give you the 2 pictures, I don't think you would be able to distinguish, unless you know what the IFS error structures is, which one is really which. So they predict things which I didn't expect them to predict.
Florian, just for listeners who are not so familiar with how this all operates, can you say how this machine learning model, if you call it that, what is it based on? What's the, without obviously going into mathematical detail, but what's the kind of overall approach that's taken?
So the overall approach is that we take error 5 data as a starting point. We sort of construct a graph, or traditionally more a grid. Our graph is sort of based on our current modeling, so reduced Gaussian grid, and then we just train, or we just optimize weights between the inputs and outputs. We do this first at error 5, and then we use those weights, or those training things, and I think it was very well explained by Amy in your last podcast, to be really fair. We use, instead of error 5, so we've trained those weights, and then we use the real-time high resolution reanalysis and train again. And because we have a better starting position, it allows us to train faster for the high resolution in that sense. And with that, we're sort of getting closer and closer in a sort of traditional optimization way. I think if anybody ever has done model optimization or calibration, it's really exactly the same process.
So the one phrase you haven't used, but I'm sure it's embedded in what you've said, which is neural networks.
No, I haven't used the word neural networks because I think it's sometimes a bit misleading as a category to be used, to be fair. And I don't think it matters so much, to be honest.
Okay.
You're optimizing a model, whether it's a neural network or a graph or whatever else it is, it doesn't really matter. You optimize weights and you're trying to get better in that as a simple structure. What
Yeah, well,
matters is what data you feed in and what data you train on. That's the real key in these operations.
so that's a good segue into what I wanted to pick up next, which was about this training data set, which, as you've mentioned, that is a crucial part. We need to know about, in a sense, the past weather data to allow the machine learning, the deep learning, to learn something about the way the atmosphere and the weather systems work. I guess again for those who are not quite so familiar, you've used the term reanalysis several times already. What exactly is reanalysis? How is that? What is that in terms of the training data set? What is it exactly?
So a reanalysis is basically a representation of the Earth or of the Earth system itself, trying to feed in all the observations we have and trying to make as seamless maps in time and space as possible. So a map without a gap. So assume now we have observations, which may be very sparse in some regions. We're trying to build, we're feeding a physical based model in between, and with that, we're sort of trying to predict the entire state of the atmosphere for every hour from the 1940s until today. So it's a very continuous time set in that sense. So that's sort of the input into the current versions of machine learning models.
Okay, and you mentioned there, and I just wanted to make sure we fully expose that of course the observations are relatively sparse, particularly as you go further back in time, and so you need what is essentially the traditional physics-based IFS to, very crudely put, to fill in the gaps between the those sparse observations. Is that a fair perspective?
I think that's a fair perspective, the current state of the art.
Okay.
However, I honestly do not really see any reason why this could not also be achieved with a machine learning model as such. I think it's entirely feasible
Okay. Well,
in the future to create something similar to a reanalysis. One
perhaps
has
we'll come on to that a bit later, maybe. So, as you said, you've used this term ERA 5, which is the European Reanalysis version 5, I guess. It's in some respects relatively coarse resolution. You said it's sort of continuous in space and time, but the resolution in space is relatively coarse, about I guess about 30 kilometers or something like that. And I know, for example, that it takes quite a lot of computing time and effort to produce that, as you say, 50, 60-year record of past weather with that, with the model and the observations. So what are the plans? I think you've got plans to upgrade that and to develop it further. What are those plans?
So one has to be careful. ERA 5 is good because it's consistent in 1940s, but as I sort of tried also to mention, we're using operational analysis, which is at 9 kilometers. Of course, we can only do this up to the last model cycle upgrade. So there's a sort of bit of a mix. ERA 6 will enter production this year. So the next version of the reanalysis will enter production this year. It will be high resolution, but I think the key is it's this one-way coupling, which is sort of a bit, we were discussing this a bit, it's a bit of a geeky thing, I have to admit, because I don't think it's something which sort of, in general, is that exciting, but I find it super exciting. Anyway, I think it will allow us to produce a better reanalysis where these relationships between physical variables are better represented and therefore should make it easier for machine learning to pick this up. However, and here comes a bit of my caveat, there's member states of ECMWF such as Sweden and Norway who are already experimenting with a higher regional reanalysis and sort of nest that regional reanalysis into global reanalysis, and by that train a machine learning model on a much higher resolution already. So there's already effects which sort of go beyond that ERA 5 reanalysis. I don't think ERA 5 is the only thing which most organizations use anymore for machine learning at the moment.
I don't think you said what resolution ERA 6 might be. Is that being decided? Yeah.
Yeah, that has been decided, but I'm not. That is something for later.
Okay.
Like
Okay.
release.
We'll hear about that later.
Yes.
I suppose, and I'll shut up in a minute, David. But I suppose one thing that strikes me from what you've just said about this training data set is that it's very contingent on the state of the modelling, obviously the state of the observations in the past, but also the state of the modelling. So we know that things like ERA are not perfect. They don't describe all aspects of the atmosphere as well as they might. I mean, traditionally people have said the tropical circulation is not so good. And then you've said, well, hopefully we'll improve on that with ERA 6, etc. What that puts into my mind is that, in a sense, the current crop of machine learning predictions then have been trained on a training data set that contains errors, that contains imperfections in the way the past weather's been described. And I'm just wondering what impact that has on the accuracy of the forecasts that come from machine learning.
So as I said, it is surprising how good they are, even if they haven't joined the things. They do reproduce some of those errors. Okay, so that there's very clear evidence that some of those machine learning models reproduce the errors which we know are in the global reanalysis. That is sort of fairly obvious. I think you see this slow. I think you're right. This was the first crop of models. It was an easy data set. It was easily indigest. It was perfect for machine learning. You couldn't get anything more nicer. It's all the same format, the same temporal resolution. It doesn't have any gaps. You don't have any messy data issues. It's brilliant for machine learning, to be fair. But it's the first crop, and you already see the first experiments popping up and news popping up where people start to mix other observations in it. It may be satellite observations which weren't assimilated into reanalysis. It may be surface observations, which sort of 2-meter temperature is currently a very popular one, which gets sort of mixed into the training data set. So although they can't reproduce some of those errors, I sort of expect also that this sort of slightly is going to be disappearing in the future too, when more and more different data sources get mixed together with ERA 5. You don't have just to stick to one training data set. You can add other training sources if you wanted to in machine learning. It's super flexible.
So does that mean if you are identifying the errors that are sort of propagating into the AI system, that then you can go back and then essentially work on those issues and resolve them?
Yes, you can. I sort of a bit hesitant because it's not that simple. I think we just talked a bit about tropical areas. And even, let's be fair, we know those areas exist and they still exist despite us knowing they exist in the physical model. And we haven't entirely yet figured out always what to do with some of them. And you have the same problem with machine learning. So even if you know what the error is, it doesn't mean it's an easy way to find this. There's no easy solution necessarily available for that.
So, but I guess we're coming to the next sort of question. Actually, it kind of relates back.
David, could I just jump in before you go on? Just another loose end I just wanted to pick up with Florian, if you don't mind. One of the aspects of the machine learning emulator model, if you will, is that it is constrained. There has to be a constraint in its design. And my understanding is that typically it's designed so that it minimizes something like the root mean square error of the description of the atmosphere compared to reality. And that is only one measure of accuracy or fidelity of a weather state. How constraining or limiting, not constraining, how limiting is it that you have to use that root mean square error minimization in the design of the model, the AI model?
What we're getting into here is a very traditional optimization problem. The optimizing against a single objective function, such as the root mean square error, is what we traditionally always had in any type of optimization exercise. So that's not something novel here too. Huh? So I'm just saying this is actually a very fairly old problem. There have been many approaches in the past trying to sort of mitigate that. And root mean squared error does have certain problems, such that it tends to end up with smoother fields, as we know, so less active fields. It does, depending on how you've designed your machine learning algorithm, so how the way you go about propagating in a time has a larger or or not so large effect on it. However, if you look at some of the activity profiles, so how active is the model, the machine learning model in comparison to reality, you will find that there are some of them who are actually now very good and equivalent active or equivalent vibrant, what you would find in a traditional physically based model. It is true, but of course, don't forget you don't have to use one single measure. If you would design an ensemble, you would choose something which is more ensemble. So it would be something called the continuous rank probability score, for example. That would be one of the measures you might be using to optimize it. And even if we nowadays implement physically based models or decide on operations, we don't decide on a single score either. We look at a large number of scores over areas, but also different types of scores. And I don't see really why this could not also be done in a machine learning type framework in some way or form. So I think we have analogous problems there, but it's true that particularly the early machine learning models had far too smooth fields. So you could really see the pictures looked very smooth and nice, whereas the world looked a bit more rackety, to be really fair to reality. That is sort of slightly disappearing. So they're getting there at the moment to represent this, and there's now quite a lot of examples. Also, when you start browsing the web, you see people analyzing these machine learning models we have on the web for different extremes, and you see that some of them have done actually extremely well for tropical cyclone predictions or extreme precipitations. Better than you would have expected, because the argument was always they can't represent extremes because they only do a medium state. I'm not sure I would subscribe to that argument anymore. I don't think the evidence is that strong.
I think that maybe leads to this follow-on question is to, with these various experiments that are going on, do you think that this adoption of an AI model for operational forecasting is going to kind of lead to abandoning physics-based forecasting, or will it always be a blend?
I think it will always be a blend because we always done blending. Don't forget, even when we now call our seamless model, our seasonal models exist perfectly fine next to our shorter range models in a way. They're always blended. They're physically based models, but they're still different in nature. It will be a blend. I think it also depends a bit what you actually are trying to achieve. I think you quite carefully and rightfully phrased it around forecasting. Physically based models have other purposes too for science, which are not just forecasting, understanding, tracing, whatever else you want to do with them. Machine learning models, AI models will allow us to create significant larger ensembles. And we do know this is one of our real problems if you want to try to catch the outliers. So get the real tails of the distribution. Physically based models, we will never be able to run the tails probably to the amount of ensemble members or to that resolution we require. That can be done, I think, with them. Physically based models, don't forget, many of the machine learning models predict a very limited number of parameters at the moment. So many of the mesoscale products I was running this morning, it was foggy. You don't get currently fog out of any of the machine learning models. Will it be possible? Maybe, but maybe it will be a physical post-processor of the machine learning model itself. So you're sort of turning the roles a bit. Rather than having a statistical post-processor, you have a physical-based post-processor. So that produce a fraction of the products, but they are significantly cheaper. I can currently, when I run an ensemble member, it's around $90 or 90 euros, and a single machine learning model costs me less than a cent to run. So you sort of see all the dimensions allow me to do very different things. So I don't think they will replace each other, but they have different purposes.
Could you just elaborate a little bit on what you said about the ensemble and enhancing the sort of the tails of the distribution? Because I think this is quite important in terms of how, first of all, half the world is still not using ensembles. and really still thinks the world is a deterministic place, which is a problem in itself. But also, when you really start getting to the real utility of the ensemble, and that is this sort of extremes, can you just elaborate a bit more on how you see the AI enhancing that?
Yeah, so there was one of those really famous papers where there was a tropical cyclone predicted to hit the US, and they calculated with 50 ensemble members, and it sort of went somewhere in the middle. It didn't really matter where. And then they run an experiment where they had 1,000 ensemble members, and one single member hit New York. One single member. It was a fairly strong prediction. Um, and I think with machine learning, well, we couldn't do these 1,000 members on a regular basis. It's prohibitive. We don't have the computer size. We can't physically. It's just not possible at the moment. Maybe if we have quantum computings in their work, they will be in the future. At the moment, it's not there. A machine learning model will enable you to more likely catch that single outlier, that small probability but high impact scenario, which would be there, which may or may not, depending on your risk appetite, change your decision what you're going to do be based on the forecast. And that machine learning model will be really uniquely doing it. What you've seen in the moment is many of the machine learning models just producing PDFs, such as probability distributions, rather than forecast traces, so that they're not really representing any temporal and spatial evolution. That is currently changing too. And the moment you have that, you sort of will have that in addition. There's one other thing. Don't forget, assume now I've run my machine learning model. ECMWF runs it 4 times a day. I've run one, let's say 12 o'clock at night, and I had this single trace which is actually hitting New York. I wouldn't want to wait for 6 hours to run the next one. I probably would like to do it the moment I have more meaningfully data, maybe an hour later, 2 hours later, 3 hours later. With machine learning, I could just very quickly spin this up and do exactly that scenario again.
I'd like to just follow up on a couple of things you just said, actually. On the speed of the predictions from AI, you said it was very fast. I just want to slightly temper that, maybe, because the machine learning prediction has to have initial conditions to start the forecast off. And up to now, I believe, we still use a physics-based modelling of data assimilation approach to produce those initial conditions. And that takes some considerable time to do. And of course, in the first place, the machine learning model has had to be trained using a very expensive, computationally expensive production of a training data set. So is it slightly, are we slightly kidding ourselves that it's so fast with these AI models?
I'm not so sure. And there's 2 things I would like to say. That of course, we may be moving in an area where we have more continuous data assimilation. So we do actually have more often initial conditions than we have now, and even would run forecasts from. B, we're currently sort of assuming that we still need a physically based model to produce initial conditions, while there's already quite interesting research out there which actually produces directly from observations, so which comes directly from whatever comes into a forecast. So I don't think that is holding very long either. And don't forget, the speed of a single model trace allows us to run 1,000 ensemble members, which is not necessarily the case. So a machine learning model on a CPU, let's say it's for comparison reasons, is run within minutes at the moment. So of course in GPUs it's seconds, but it doesn't really matter. Whereas the single ensemble takes 10, 15, 30 minutes to run in that a single trace. So the speed matters. It's just not
Sure.
in the way you see it. I think it just gives us new capabilities which we didn't have at the moment, or don't have at the moment.
So if can I elaborate a little bit, because it came up in some questions of colleagues who are using ECMWF products and are concerned that at the moment they're getting a few outputs a day, and it's in between those outputs that you really have all the action. And so there is a kind of obvious sort of follow-on from what you've just said, is that you're able to really do a more rapid update cycle using machine learning. I think that seems to be a very valuable aspect of this solution. Would that
I
be
think it
correct?
will allow us this type of hybrid system. As you said, as I said, I started off, it will always complement a physically based system. But I think the configuration, I think exactly what you just said, it will allow us for configurations which may be more tailored to certain users. I'm actually not saying that every user can deal with that or even needs that. But I think there's a few who would need that. You could
But
take this one step further, David, in a way that those users you were just talking about, they could run their own forecast however they like because they're so cheap to run. They wouldn't have to wait for ECMWF to dispense its data. They can just do it on their laptop.
okay, I guess to pick up and to move on to something that you've hinted at already, but very recently ECMWF have announced a research project at ECMWF where you're going to experiment with only using observations for both the training data set and for the initial conditions. So in a sense, this cuts out altogether, in principle, cuts out altogether the numerical weather prediction, the physics-based numerical weather prediction model. And so it sort of suggests two obvious questions. Are those models going to become redundant? Because that is that will be an incredible transition. And I guess a second follow-on from that would be, what is going to be the implication of that for science, for our understanding of the atmosphere and oceans, if we're not actually using physics-based models to predict the future?
I think this is a really good question, and it's true that we're doing this. Don't forget, our strategy was always sort of based on three strands. It was on machine learning forecasts, as you currently see. It was on replacing parts of the physical model with machine learning, and then it was of that what you just described, which was the observation directly to forecasts. This is a very still research question at the moment. So it's at the very, very early stages. And the training of using of observations has a huge amount of challenges. It's very similar to the challenges we have. How do we use them with additional modeling? As we know, there's lots of different types of observations, lots of different sources. They tend to be unstructured, they're messy, they have missing values. Some of them capture something physical, some of them capture something which is sort of a derivative of physical, so we sort of need to have an interpretation of that. So it's actually quite a messy business. That's sort of why the reanalysis was so popular, because it's so simple. Observations are super messy, and we know they're messy. And then they come in and they come out, and there's never a consistent record, and the errors change and whatever else happens. So it's actually quite a researchy question. I think there's quite a lot of. I think I would be currently very quietly optimistic. So there are some, if you start, let's say, restrict your observational space to satellites only. So you start with satellites because they're sort of I would argue, the least messy. I don't know if that description fits compared to many others. And you sort of can see that you can actually start to use this in a sort of a traditional data simulation that way. So there's ways for optimism. It is an opportunity, but it's also a massive challenge too. So we need to see how far this goes. So I wouldn't actually currently go as far as you said that we're going to replace those physically based models. Again, I'm just coming back to what I said. These physically based models have more purposes than just forecasting. Forecasting is one simple or single application. It's not the application. Some of them are for understanding the science and the research. And for that, you always will need that model.
Yeah, I mean, I absolutely agree. But if you think about the scientific method, I mean, the scientific method is about making hypotheses about how the world works. And then to test that, you have to make a prediction based on your hypothesis of something, whether it be an experiment or be, in our case, the future weather. So actually, I've always thought that the operational predictions were a crucial part of the science. You know, that they're the part where you can demonstrate that your scientific theory or hypothesis is correct or can be disputed or refuted. So one of my worries is that if we don't continue to run physics-based models for prediction, then we will start to lose the the challenge that provides to the science. I mean, it's a slightly separate question than for an operational centre, I accept, but it's I just wanted to make a comment about that. But related to that, you've used the term hybrid and complements quite a lot through this conversation. You know, the physics-based modelling, traditional NWP, and the machine learning will work together in a complementary way, in a hybrid way. I don't really understand what that means. It sounds nice, warm and fluffy, but what does it actually mean? Does it mean that we have to run two systems, whereas previously we only ran one? Or how does complementarity, what does it mean for you?
So I think we will be running two systems for a while rather than just one. I think that is very clear. And I'm sort of slightly hesitant to make a prediction what the proportion of those two systems would be like, because I don't think any of us would have been 2 years ago predicted that rise of the machine learning to the extent we're seeing it. I think so. I'm sort of a bit hesitant. So I think they will always be complementary. As I said, they may complement each other in frequency or in ensemble member size or in the types of parameters also forth. There's many ways where they produce slightly different outputs, or one you could derive one from the other. So I think that's where the complementary element comes in.
So does that if we are running both of them, notwithstanding the fact that the AI system runs quickly, it's going to put a bigger requirement for more supercomputing resource than we have today, won't it? We have to run two systems instead of one.
Yeah, we have to be. So I don't think for the operations it necessarily mean that. However, and I think that's where the big if comes in. Don't forget, a lot of the time or the cost of a machine learning model, actually even of a physical-based model, is actually in the training. It's not necessarily the forecast. The operational forecast compared to what we invest in research, computing-wise, actually the operational part is dwarfed compared to that, and that's the case for both. I think what it means may be slightly different computing systems. If a model, if you have a machine which you primarily use for research purposes, there will be a different level of operationality you need of that particular machine. And we all know that the more operational a machine gets, the more expensive it tends to get. So you may be able to move to other types of systems that are bigger. The second impact will be on the archiving the data. A machine learning model at the moment is able to produce data so fast that you have an issue with archiving. So there's an idea how you change that. So there's a lot of implications that still go significantly beyond the size of the machine. So I'm actually not so sure that size will be the limiting factor. I think it will be somewhere else in the data pipelines where we have issues.
One final comment from me on this before I hand over to David. I think one of the aspects, I think you've mentioned it actually, one of the aspects of currently machine learning predictions is the time step is 6 hours, I think. And I think David mentioned it, that users want much more frequent information than that, because they want to know, what's going to happen in the next 15 minutes or half an hour or an hour. Why is there this 6 hour time step, and what's the implication of changing it?
I'm going to give you my interpretation of it. I'm not entirely sure it's true. I believe it is because the ERA 5 data are archived, easily accessible on a regular grid of 0.25 degree in a 6 hour time step, and it's easily to download. And that is actually why most of those models are exactly that configuration. I can find no other reason. We have hourly data. You could use hourly data, but it's easier to demonstrate and test on 6 hourly data. There's not really any reason apart from at the cost of training why you wouldn't go to hourly data.
I mean, traditional NWP, because of the time step, which is much shorter, of course, there's an accumulation of error associated with every time step. There's a bit of error which then feeds into the next time step, and that grows. So isn't one of the reasons that the AI model is so fast is because you're only doing it every 6 hours and you're accumulating less error, whereas a traditional NWP model is operating much more frequently, and consequently it accumulates more error.
I wouldn't subscribe to that. I'm not so sure that is true. I'm actually I don't think the time stepping is the difference why they run faster. You could run the model in a much lower time, so it will be still significantly faster. And the error accumulation is correct, but I don't understand. I don't see any reason why this shouldn't be equally be solvable in a machine learning sense as it was in the physical sense. I don't see why you couldn't have similar constraints. It's just about how you put the constraints into the functions, to be fair. So I don't see that as a significant difference. You
Okay.
know that the time stepping our model is also much higher, but we only archive every hour or every 6 hours, depending on where you are. So even the physically based models are actually the time step of archiving is dislinked. I still maintain the reason why the configurations are as they are is because error 5 is archived in an easily accessible way in exactly that type of format.
Can I come back to one thing that you said earlier, and it had to do with your experience with fog. So, and it kind of touches on this whole notion of, where does the future understanding of the physical system end and other things take off. And I'm just curious. You said specifically that I think that post processing would be the way to pick up some of these processes which are not captured effectively by the machine learning or necessarily by the current physical models. And I was just thinking, how does that actually work when those physical processes should be interacting with other aspects of the physical system? I mean, cloud physics obviously is doing so. And therefore, how are we going to have an advantage of doing this sort of post-process cloud physics activity, for want of a better word?
Yeah, maybe cloud was not the best example, but please don't forget, we have a very long tradition of adding impact models to our meteorological
Yeah.
model, which
Yes.
also in
Yeah.
theory should be interacting, but they don't. We've
Yeah.
attached cities, we've attached hydrology, we've attached agriculture. All of them theoretically also should have interacted with the atmosphere or the Earth system model, and they didn't. And we
Yeah.
still saw value in
Yeah,
doing that. I
I
think
guess
that
the cloud physics, the cloud physics one was a little red flag because that's what I had used to work in once upon a time, and it's sort of like we really thought it was an integral part of the system, and we do know that it's a problem that still hasn't been entirely solved, and it remains a physical process problem that we really have to work on, and you don't want to lose it because suddenly we don't need to do that anymore. But I think that's not what we're saying anyway. I'd like to kind of move on to we do a lot of our listeners and viewers are from the developing world, and we interact a lot with developing country Met services, and one of the challenges they face, of course, are limited budgets, limited and very limited human resources as well. And yet many are busy continuing to develop traditional modeling systems. I mean, utilizing the kind of tools that are available and are only just sort of beginning to look at the potential for AI. And I guess what I was wondering is, how do you think that they could be employing AI tools to actually really exploit ECMWF products more effectively? I mean, what if you were to give advice in terms of what direction a country should take with limited resources? What should they focus on in this world of machine learning?
we have been talking a lot about machine learning now for the weather model itself or for the forecast model itself, but machine learning will impact every single aspect of that forecasting chain. That goes from the inputs, but also goes all the way to the warnings and the impact modeling itself. So I think that's actually where machine learning may have a significant impact, which we sort of didn't touch on. In terms of running weather models, one has to be a bit careful that machine learning, you don't necessarily have to have this additional chain of global, regional, downscaling type approaches. You can use something like stretched grids, and Met Norway, for example, is one of the countries which currently does that, which sort of use the same infrastructure as we use for our global model, but then refines that model or the data over the area and then actually optimizes a global model while optimizing a sort of limited area model. So that's that you have to slightly break out of the current cascade of modeling there. And of course, that will be possible for nearly any country. Don't forget, in contrast, maybe to many physically based models, most of these machine learning codes are now open source. So there's very clear, very low barrier. However, they cost an absolute fortune to train. So you will need a cloud or GPU cluster type provision to train those models on your specific data, and you will need the expertise for that. So these are not problems which are sort of different to what we have now, just now we have them with the physically based models. The concepts are sort of all striking the same. You can run a forecast in a box. So we call this model in a box, where basically you sort of get everything, you get sent the initial conditions and you start your own forecast however you like it. So it's a very low cost. If you have a beefy gaming computer, you can run a forecast. So you don't need an HPC anymore with machine learning. So it becomes a far cheaper, lower entry barrier. That means for anybody in the world, no matter where they sit on the globe, they could run their own forecast and produce their own forecast and issue their own forecast. So that sort of has an implication of a role of a weather service and how that competes with official warnings. So there's quite a lot of issues in that area. And with Destination Earth, for example, with the Copernicus program, with the Destination Earth program, we developed this model in a box approach, which everybody will be able to take and do what they like. I don't think that's the biggest problem. I think it's still that we need to work with a lot of countries to sort of train them and build together with them how they actually use the things. I don't think running the model is the biggest issue. But the same way as I don't believe that running currently a limited area model such as WRF is really a big issue. I think all the other stuff around it and stuff is, I'm using it a very wide phrase here, is I think the real problem. So I don't think it's gonna crack the nut or it's gonna be the game changer for everything. It just will make it cheaper in that sense to run.
Just to follow up a little bit and come to a sort of maybe a specific example of create a kind of scenario. So we were talking about 6-hourly ECMWF output. So many countries access that and will have even more access to it, I guess, with the future system that you mentioned at the beginning. What would be the first thing that you would want to do? You as a user in a developing country are really looking at short time steps. I mean, you're looking between these large 6 hours. You want something in this window. The use of AI seems like it would be very useful for that rapid update cycle, which we were talking about. And is that technology, is the technique rather, already available? Is it something that would be a lot of learning to implement that sort of system? What would be the way to go about it?
Well, the technique is nearly imminently available. As I said, it's already used by Met Norway. We will be releasing all of our code as open source, and it will be available. The challenges will be to arrange your data for the training in a way so you can actually do the training.
Okay.
So you need to sort of plug those specific data in a machine learning ready format into that, and then you need a big enough cluster of GPUs to train it. So that is where the real challenge is. If you have done that, or when you have done that, it will be fairly simple from there on.
Okay.
Then it's not very complicated to run a machine learning model. It's really a one-line execution, and it comes out. You still have the issues that you have to have an interpretation of the results, and you need to carefully think what those results mean and what you do with them as you have it now. So that is sort of very the same as you have it currently. Running the model itself will be very, very easy. Constructing the model is where the skill is going to lie.
You talk about interpretation of the output, and I just wanted to finally ask about that. I mean, forecasters, operational meteorologists today add a lot of value to the numerical weather prediction data output by interpreting why and how the weather evolves the way that it does. And this is a sort of area that, traditionally people say, well, machine learning is just a black box. We don't know how it actually produces the results that it does. And so we can't really figure out why something happened. In our case, why a weather system developed in the way that it did, and why perhaps one could interpret it to develop slightly differently. So the sort of explainability of how things evolve seems to be less with the machine learning model. Is that right?
I'm going to challenge you a little bit on this one. If a forecaster would like to understand why a weather system is as it is, are they going to rerun the model, or are they going to look at other outputs of trying to find interpretation of why it is so? Are they really going to rerun the IFS and trace exactly back what they're doing? A forecaster. I'm not talking about a model developer, a forecaster. I would actually say they don't. They look at different outputs. They will look at outputs of different models of all different sorts and will find interpretation. They're not going back and trying to say, if I increase the soil moisture in Eastern America at the moment, it will get that temperature, and therefore it must have been that soil moisture.
Okay. Of course, the model developers develop the model as a result of the forecasters saying that there are interpretation issues with the forecast or problems with the forecast. So that there is a feedback loop there, isn't it, between the forecasters and the model developers, so that they're not entirely independent of one another.
No, they're not entirely independent, and there's a feedback loop, but that feedback loop also could go to the data. You could also figure that out from the data themselves. I don't think it's just based on the physics. I'm not saying it's not done. I'm just saying that a forecaster calling a machine learning model a black box while calling the IFS our model not a black box I find it a slightly unfair comparison, because the IFS is also a black box in that sense.
Just to be clear, I wasn't saying that a forecaster had accused it. I'm just saying in general, AI is often commented on as, and we had this big summit in the UK on the sort of regulation and politics of AI. And one of the key things was a concern that AI methods don't have the same level of explainability as other ways of doing things. So that was just why I was raising that point.
You're right. There's a huge area of ethics which needs to be addressed in machine learning models and machine learning and forecasts. And I think it gets even further if you think that maybe a forecaster's job will change and they won't do exactly more what they do now, and they may not have the same way of interacting with the data themselves. But that's nothing new. When I came to ECMWF, we were still hanging up A3 sheets of paper in a big wall and trying to make interpretations. That is gone now, I think. I know.
That's good
you may have had your part in that, Alan.
That's right. Yes, absolutely. Look, Florian,
can I bring before we close? Can I just? Okay. I wanted one other question. It comes back to the sort of data to forecast direct link, right? So using machine learning and taking observational data, there is there's a lot of investment being made in observations and being made in. I mean, there's one area then everybody is trying to do more and more in terms of observational capability. A lot to feed into ECMWF actually, so that you have the data to put into the operational system. But would I be right in understanding that through these machine learning techniques that we could actually make even more value at a local, so from a local data collection perspective in a national context, that we could make more of the observational data as a result of having access to machine learning tools and going direct from the observation to the forecast in a more sort of analytical way than we have done in the past.
Yeah, and I think it goes even further. I think that the value of local observations, machine learning, may be even higher, because you can actually more directly link from global because of the stretched grid, from a global to a regional or even a local element or resolution in that sense. Machine learning models will be even more hungry for data. And whatever we're going to do in the future, whether machine learning or not machine learning, we need more data. And that's why I'm eternally grateful for all of those countries who actually provide more data. And that's why I'm so keen, for example, to support this WMO SOF initiative, so this systematic financing of observations, because we really need more observations. And I think it's only right for them to ask then for ECMWF data to come back to them in a free and open way.
That's a great way to conclude, I think, our WeatherPod episode. And Florian, thank you so much for sharing your thoughts on this and how this very dynamic field is now evolving at ECMWF and more widely. So there's a lot for us to consider in what you've said. So thank you very much.
Yeah, thanks, Florian. Thanks. Really interesting. Thank you. Well, that concludes this episode of the WeatherPod. We hope you've enjoyed it. Alan and I will be back next month, and in the meantime, please give us your feedback via email to support@gweforum.org.